Hi, welcome finally to Act 2 of Hi Jax. So this is Lecture 6, Hi Just-in-Time Compilation. And actually this whole Act 2 is going to be about just-in-time compilation. But in this lecture we're going to meet just-in-time compilation, some of the basic properties of it, and basic concepts that we need to understand JIT in JAX. And so the way we're going to do that is basically talk about accelerating our existing SimpLeNet implementation that we've been working with for the last few lectures, and we're going to compile it and then see that it runs appreciably faster. But before we get into that, we need to learn some basics about JAX, just the first things about JAX, and the place to learn about JAX is going to be the JIT dojo. So I'm in the Hi Jax repository here, and we have this folder, JIT dojo, that has 8 lessons about JIT that we're going to work through one after another to sort of discuss, just demo in a simple example, some of the properties of just-in-time compilation. And today we're going to work through lessons 0, 1, 2, and 3. And then in the coming lectures through the rest of this act, we're going to work through the rest of them to see some more nuances of JIT. But today, let's start with lesson 0. So this lesson is actually really not about JIT. It's just a set of baseline, and I'm going to just talk through this very simple plain JAX function that has no JIT, and everything is going to be exactly as we expect. And we're going to do this because we want to have this as a baseline when we compare this to the behavior of this program to the behavior of a program with JIT that is going to be a bit more complicated. So let me just take you through the function that we're working with, and then explain what is going to happen. And I'm going to start by running it. So let's run Python lesson 0, and you can follow along if you're in the Hi Jax virtual environment in the JIT dojo folder. You can run lesson 0, and then you can play around with the values if you like. So okay, so we're just doing some basic imports here of JAX NumPy and some JAX typing things, but the really important thing is that we're defining this function, and so this is the first thing that happens in the script. Defining a function f_no_JIT, and so that's not super exciting. We'll talk about the function in a moment. And then we're printing out that we have this pointer to the function that Python renders like this. Okay, so then we're going to call the function. So we should look at what's actually going on inside the function. So we're going to call the function with some arguments, an a range of size 8 and a ones of size 8, where we specify by default the type of this will be float, but we're going to specify that the type should be int. And then we're going to go in the function and evaluate it. So let's look in the function. This is sort of the order that Python will do things in too. It will sort of, when we define the function, it won't look inside, but then when we call the function, then it's going to look inside and the interpreter is going to evaluate what's in there. So, and that's what we see happening here. It's going to evaluate this print statement and then print out f from inside f, the value of a is, and then it's going to print the value of a. And so look what we see here. So it's printing the value of a, which is what we expected. This is just a range 8. And then we're going to go through and print the value of b as well. And so that is what we expect. It's just some integer ones, just an array of ones. Okay, and then the next thing the function is going to do is add these two arrays together to create a new array called c, and then print out the value of c with this arrow to indicate that this is like the result of the function that's about to return. You can see that that is just the a range plus 1 element-wise, and we get what we expect, the numbers 1 through 8. And then we return c, and then no surprise, that is what we get printed out. So once again, no surprises here. But keep this in mind because this is going to be the baseline, and we're going to get a little bit more interesting now with lesson 1, where we're going to do some JIT. Okay, so now we've imported JAX so that we can have jax.jit, the function transformation that we're going to be learning all about in this act. And so lesson 1 is just-in-time compilation. So now we're going to define this function again. And so we define the function. That's fine. Oh, actually, no, I need to call this lesson 1. We define the function. That's fine. Step 2, transform the function. So we're going to transform the function. We've seen this in the overture. To transform the function, we just need to call jax.jit, pass in the function. It's going to return a new version of the function that is just-in-time compiled. In reality, this is just a wrapper, and the compilation happens later, as we will see. We saw this in the overture. We're going to print out the object that this gives us to sort of show how Python is going to represent it to us, and we'll see that we get a pjit function object of a particular function object. And this is the rendering of the same thing we had before, and you can see it's even the same pointer. So hex 105f, 105f, and then so on. Okay, so then notice that we haven't gone inside the function yet anyway, because these prints haven't triggered. So up till this point in the code, we haven't gone inside the function. That's going to happen next. We're going to call the function. Now, we're going to call the function with similar inputs to last time, JNP arange 8 and JNP1s 8 with dtype int. And so this should go inside the function. If it was a normal function, it would go inside, evaluate all the print statements, compute the sum of the two inputs, and then return it. But what happens here is a little bit different because this is a JIT function. This isn't fnojit. What happens here is you can see by looking at the output, and we can kind of try and reconstruct what's happened internally. So the output here is that when we get up to this print statement, the value that comes out isn't JNP arange 8. It's not an arange at all. In fact, it's a completely different object. It's not even a JAX array. It's a JIT tracer object. And so this stage is called tracing. And so this is when, as I said in the overture, JAX is going through with abstract versions of the inputs that just know their data type and their shape. And they don't know any of the values. But they do accumulate all the different operations that happen in the function, and that gives it the computational graph. Then that stage is called tracing. It sort of traces the outline of the computation, I suppose. And then it's going to compile that and sort of format the computational graph in a more efficient way and for the hardware. And then it's going to actually run it on the hardware, whether that's, in this case, a CPU, because I'm just installing JAX on my laptop, or it could be a GPU or a TPU. Now, so this JIT tracer is one of the objects that is doing that computational graph accumulation. And we're seeing it, we've kind of caught it in the act of doing tracing now, and it is printing this out instead of the array that we know is going through in the values later. And then what about this next print? Then it's the same thing. We've got the JIT tracer for this. And then when we do this plus operation, we get an object C. We can see that C is also a JIT tracer. It is the sum of two JIT tracers must be a JIT tracer. And that is basically how this computational graph is built. And then we return a JIT tracer as well. So, but that's not what we print out, because obviously in order to actually get the output of the fjit command, it must be that we at some point returned a JIT tracer, but that was during tracing. That wasn't during execution. And so the JIT wrapper, the JIT function, basically gives us a function that is going to do this multi-stage process of when it sees some inputs, it's going to first trace through the function with abstract versions of the inputs. Then it's going to compile the function, and then it's going to execute it. It's going to take the output of the executed function and return that to us. When in the tracing stage, it is going to take the output of that tracing thing. That will be the JIT tracer that represents like the entire computational graph and all of the outputs of the functions, because this will sort of have a track of all of the operations that were used to implement that output. And so that is sort of what's going on here. We've seen an insight into the tracing stage. But then by the time we see this result, a lot more has happened. We've done compiling and then we've done execution. And importantly, the last thing that I want to take away from this before we move on to the next lesson is that we did not see the print statements happen at any stage during the execution. When we had the actual values going through this function, they did not hit print. Otherwise, we would have seen something being printed out. And so what's going on there is that these print statements, they don't enter the computational graph because they don't produce a JIT tracer object. So they don't get recorded in JAX's log of what is going on, because there is no thing about the return value that is sort of influenced by those print statements. And so when in the overture I said, look, JAX functions have to be pure and they can't have side effects, it's actually the case that they can have side effects. It's just that the side effects will only happen once at trace time, which actually only happens basically the first time you call the function, or maybe sometimes it happens again. We'll see that in future lessons. But things like printing out is only going to happen at trace time. And so it's more accurate to say not that JIT functions can't have side effects, but if the functions that you're going to JIT have side effects, those side effects won't stick around for execution, and they won't be actually repeated every time you call the function. They're sort of only going to happen whenever the tracing actually happens, and that's less frequently. So that's good to notice. And now we're going to move on to lesson 2. So it would be cool if we could find some way to see what is going on during the not only the tracing stage, but also the execution stage. And so that's what this lesson is about. And so we're going to have a look at this code, and then we're going to run it, and then we're going to see if we can, again, reconstruct what has gone on in the code by looking at the output. So here I've got, again, the same sort of inputs and the same kind of function. It looks a little bit longer and more complicated, but the only differences here are 2. So it's the same jax.jit wrapper. Oh, did I also not explain this? Oh no, this is the first time we've done it like this. So I don't have a separate defining and then transforming the function section now. We've done this sort of in a more idiomatic way, where I use jax.jit as a decorator. Now remember in the previous lesson just now, we had fjit equals jax.jit of fnojit, and so we had this entry, and this created a new function in our namespace, fjit. But this is basically what a decorator already does for us, is it takes a function, and as you're defining it, it redefines that definition to have the version of that function passed to the decorator, and the output of the decorator becomes the function that enters the namespace. That's just how decorators work in Python. And so it's perfectly idiomatic Python and perfectly idiomatic Jax to write jax.jit as a decorator like this. And it just basically means whenever you call this function, it's going to be the JIT wrapped version rather than the no JIT version, which is how it's actually written. Okay, so that's the function, and now it's defined and transformed kind of in one go, and you can see that because, I guess I might as well run the code now. And you can see that because when I define and transform the function, the version of the function that I print out is the pjit function of some inner function that was like nameless, and it was defined, well, I guess it was named f. It was defined and then captured by the decorator, and the thing that entered the namespace was actually the pjit function version. Okay, so now let's look a little bit inside the function. Now, I'm saying this is the same function as before because we have our print and our sum and our print and our return. We have these extra lines of jax.debug.print, jax.debug.print. And also, I've made sure, now that we know these print statements only happen at tracing time, I've kind of clarified that in the outputs themselves. I'm saying, when you see this message, you know that it's from f.trace. It happens during tracing of f. And then these f.debug, they happen during sort of execution, and the jax.debug library allows us to attach print statements to the computational graph specifically so that they will happen during execution. So it's very useful, actually. So I've added these. For each print statement, there is now a version that happens. It's a normal print statement. It happens during tracing. We know that. And I've added a second version that happens during execution. By the way, it's worth showing that this is not exactly a normal print function. It's more like a format function or something like that. So the syntax here is not like print. You can't just put in an arbitrary amount of stuff. The first argument has to be a format string. And then the later arguments have to be the values that you want to look up, the current value of those during execution, and put it into the format string in the positions that you get. So here what I've done is I've said I want to print out A, and then I want to put it here. And then I've said we want to print out A, and it should go here. This is like old style printing in Python with the .format method on a string or something like that. And so whenever you're using jax.debug.print, this is how you're going to want to use it. Anyway, so what's the effect of this? So when we call the function, we already know that it's going to go, we've already hypothesized that it's going to go through this sort of tracing phase, and then the compilation phase, and then the execution phase. And we can see that happening here very clearly because of these debug print statements. And so let's have a look. So we've called the function with JNP arange 8 and JNP 1s again. So this is similar to last time. And now the output we've got is different. We've got the same output as before in that the first things we see are these JIT tracer objects going through the function and hitting the print calls. And notice that they're actually not hitting the debug calls, or maybe they are, but it's not printing anything yet. So that's fine. This is like before. But then previously we went from here just to the result. And now we've managed to capture something that happens in between with these debug prints. So these debug prints have captured, you can see they're coming from the debug prints because we've got f.debug. We're capturing actually the values that are going through the computation. And we're capturing the inputs, and then we're capturing the output before the return. And that's coming from these debug prints. And so this is happening at execution time. It has to be execution time because that is when the values are actually available. And so the function of debug print is, as I said, when you're building the computational graph, when JAX is tracing and it sees jax.debug.print, it adds a special node to the computational graph that says, okay, when we're doing this on the GPU, hold up a second when we get to this point. Get the current values, make sure they're all computed and there's nothing like left to do lazy, left lazy or whatever. Make sure they're all ready, and then send them back to the user in the output. And so this is going to slow down our computation, obviously, to sort of have this be something that we do on the way while we're doing the computational graph. But extremely useful when it comes to debugging, because this actually gives us the ability to print out the values as they are being computed on. And I don't know about you, but if I wasn't able to print out values inside a function in order to debug it, I would be completely lost. This is a super useful thing to have available. So I'm glad that this feature exists. Anyway, so I think we now have sort of an understanding of what happens when the first time you call a JIT function. And when you JIT the function, it doesn't do any compilation, but it just wraps the function and it's sort of preparing it to do compilation. And so it's ready to do compilation the first time it sees inputs. And when it sees inputs, it will then trace the function to figure out the computational graph. It keeps track of the data types and the shapes involved and all the computations. Then it compiles that computational graph, and then it actually executes it. And if we want to see what's happening during the execution, but before the end when we see the final result, then we have to use jax.debug.print, this extremely useful JAX function. Okay, there's a few more things here, and this number 3 is just to make a point. When we call the function with the same types again, it's not going to trace it again. It's only going to execute it. And we can see that here because there was no more ftrace calls. And we already saw this sort of intuitively in the overture in that the JIT function, the second time we called it, it was much faster because it didn't have to do the compilation again. So that's sort of as expected. But one point to make is that actually if we were going to call the function one more time with different types or shapes, so in this case we're calling the function with actually still integers but with different shapes on the d types. So this is a range 4 instead of a range 8. So it's still an int32 array, but now it's got length 4 instead of length 8. And likewise for these ones, we've got another int array, but it's got 4 instead of 8 as the shape. Now we can see it actually traces again, and it makes sense it has to trace again because the tracing only happened for a certain shapes for ints for d types and shapes. And so we go through with JIT traces again. So it must be that JAX, this wrapped JIT function, knows when it needs to trace and when it's already traced for this combination of d types and shapes. And that is using a tool called like a compilation cache. And so this cache is keyed by the d types and the shapes of all of the inputs. And we're going to see more about this in future lectures about how we can take advantage of this. But it's important to know for now that we want to JIT things that we're going to be calling multiple times with the same shapes and d types. And so in this case, because we're calling it with different shapes and d types, it might be that the compilation should be optimized slightly differently because maybe more things fit on in the GPU's kind of the size of the sort of basic blocks of matrix multiplications and so on. And so it's going to recompile every time you have different shapes, just in case it can find a better thing to do. And also d types, because then it has to sort of use different operations sometimes. And in this case, we can see, yeah, it's tracing again and then it's executing again, as if we were calling it for the first time. So this is also something to watch out for if you're finding your program is slow because you're calling a function with a bunch of things with variable shapes. It might be that it's actually compiling a lot more than if there's some other way that you can like pad out the shapes to make them all the same or something like that. It might be able to just compile once and get the benefit of that speed up, even if you have a little bit of an overhead of the sort of redundant space in the arrays or something like that. Sometimes that can make sense. So now let's just recap. We've learned two useful things from this JIT Dojo lesson 2. Well, we've maybe learned several useful things, but two things to take away is one, we now have this model of tracing, execution, and tracing, compiling, and execution. But before tracing, we have to put the decision to trace, which is involving this sort of compilation cache. And if we've traced this combination of shapes and data types of inputs before, then we're going to reuse the result, the existing, because the computational graph will be the same, we're going to reuse the compiled code from last time and skip the tracing step, skip the compiling step, and just go straight to execution. Whereas if we have a different combination of shapes and data types on the inputs, then we're going to redo the tracing, redo the compilation, and get a new thing that will enter that cache for next time. But the first time any combination is used, we'll be compiling, we'll be tracing and compiling. That's one thing to take away. Another thing to take away is this jax.debug.print, which is extremely useful, and I'm sure we'll find a use for it before long in our coding, and you will too in your own coding. Okay, so let's do our last lesson for this lecture, lesson 3 of the JIT Dojo. And this is a lecture that says that even though values aren't available at trace time, the shapes and the data types of the arrays are. So this is now a different function just to sort of make this point. And let's walk through it, and then we'll sort of we'll see what the outputs are and see if we can understand what's going on here. And I think this sort of follows from the kind of stuff that we have already been doing. We know we have these JIT tracers floating around at trace time, and we saw in the output that they have these shapes and data types. But this is just to make the point a little bit more explicitly. So we have a new function now, and we're jax.jitting it again, wrapping it when it's being defined using the decorator. And this function takes a single input, which is an array of some numeric type. So this could be float, int, whatever. This num is just like an abstract thing from jax typing that includes the specific numerical types. But it's got it's a one-dimensional length n array. And we're going to produce an output with the same, actually I guess this is not clear that it's the same, but I have in mind this is the same numeric type as output, and it's going to be an array of n by n. So it's kind of going to be like a square version of the input. If the input is like a vector, this is going to be like a squared version. This would be the type of like an outer product operation, I guess, or like a self-outer product operation. But what we're going to do is something slightly different. This is actually going to be effectively a diag function that takes an array and puts it along the diagonal of a matrix, and so we'll see how it does that in a moment. So here we are. So we're going to do some printing at trace time, and just to make the point that we have the shape and the d type arguments, or like fields of the array A available. And then we're going to do this diagonal transformation. So we're going to capture n, which is this shape. We're going to create a new array of zeros, which is that shape by the shape again. So n by n now. And we're going to use the d type of the original array. And this wouldn't work if these were like the values that we were using to decide the size of this thing. But it works in the case of this because the JIT tracer object that's going through, that also has a shape and a d type field. So this is going to be fine. And then we have just zeros at the moment. Now we're going to set this along the diagonal. So we know we can't mutate A. We have to use this .at.set sort of pattern. And so here we're going to .at. We're going to index in parallel along the sort of A range for the rows and A range for the columns. So that specifies the leading diagonal. And then we're going to set that to A along that diagonal. And so like I said, this is going to create a version of the matrix that has, it's going to create a matrix that has the original array along the diagonal. Okay, so we can understand that. And then we're going to, at trace time, print out whatever we know about this A. And at execution time, we're going to print out the first and the last row so we can sort of see the values going on. Okay. So what happens when we call this function, and then it will actually trace and execute? So let's see if we understand why we get this output. So we're calling the function. First thing that's going to happen is tracing. That's unsurprising. We're going to see that A is a JIT tracer, int32.4. Like I said, the shape and the d type, the JIT tracer has these fields as well, and they will be matched to whatever the input was. And so it has a.shape is a tuple with one element and it's 4. That makes sense. We were calling it with this JNP array 1, 2, 3, 4. And then this trace command, this trace print line is going to come out with a D type, which is int32. That makes sense. We see it right there, and we know that when we create a JNP array with integer values, a list of ints, it's going to sort of determine that that should be an int32 array. So that's to be expected. Okay. So then one more thing happens at trace time, and that is that we go through all of this computation and we print out what we know about the array A that we've built. And we see that it is a 4x4 int32 array. And that's fine. Okay, tracing is now concluded, and we're going to then compile and then execute. And when we're executing, we've requested a printout at a certain point that is going to be this debug print. And so that is here. And so that debug print is going to have, we've built this array A. It's got the things along the leading diagonal, and we're using two slots in the format string now, one for the first row of A and one for the last row of A. And so you can see here, here's the first row and here's the last row. And that's what we would expect if we were putting 1, 2, 3, 4 on the diagonal. So far, so good. And then, of course, we print out the result, and this is just some code to sort of indent it so it matches with the rest of the output. But we basically print out the result, and we can see here it is indeed the diagonalized version of this matrix. Okay. I think we can speed through the rest here. Now we have a floating point array that we're calling. Remembering we said that this was a numeric array, kind of an abstract. Could be float, could be int. Same shape, but different D type. And then it's going to go through all over again, but this time the D type is going to be float. And so a.d type is going to be float. When we set the D type of that's little a is going to be float. When we set the D type of big A, it's going to be set to float. So we're going to get that the output is going to have type float 32. We're going to see that happening in execution time, being a floating point version of this matrix with the first and the last row, as you would expect if we're putting things on the diagonal, and then we see confirmed that this is the output. So we were able to change the sort of computational graph to reflect the data types involved in the objects that came in as the input. Once again, tracing happened here, and then again here the second time we called the function, and that's because we called the function with a different combination of shapes and data types of the inputs, and this is using float 32 instead of int 32. Okay, so that's all of the lessons that I think we're ready for in the JIT dojo, and we'll come back in the next lecture for some more lessons, and then we'll keep coming back until we've learned everything we need to know about JIT. But for now, I think we've learned enough to be ready to start using JIT and to accelerate our program, our SimpLeNet program. So let me go back to the sort of overview of the Hijax repository. And this is lecture 6, so let's go into the lecture 6 folder. And we'll see that there's actually nothing here, once again, because we're going to copy the code that we have from last time, which you might have in the lecture 5 folder if you're in place modifying. But I've been putting my finished code in the solutions folders. So I'm going to take SimpLeNet Atom from there and copy it here under the name SimpLeNet JIT. It's actually, I guess, SimpLeNet Atom JIT, whatever. So we have this SimpLeNet JIT, and I can open that. And the only thing that's wrong about this is that the doc string here needs to be updated, and so I need to go through and update that. But basically, we'll just change it to lecture 6 for high just-in-time compilation, and we'll ignore this for now. But we have our familiar code here, and I basically just want to go through this code and put jax.jit decorators on everything that we can and see if this runs a bunch faster. But to get a baseline, I guess I should go into the lecture 6 folder, and I should just time running Python SimpLeNet JIT. And there's a whole bunch of this that is about initialization and everything, and it's going to take longer than just the training loop. But maybe we can speed up some of that too. Yeah, let's just see. It's loading up the training now. We've already seen this happen a few times, so it's not super exciting. but I'm just doing it now again to get a time. And then we're going to use this as to see what we get at the end, whether it's running much faster or not. But while that's running, I guess I can start going through and looking for things that I could JIT. I don't think I can really JIT the data loading. That is mostly just converting things from NumPy arrays to JAX arrays. So I'll just leave that. But maybe the initialization of the SimpLeNet. We'll see if we can JIT that initialization. This we could probably JIT, but yeah, let's try and JIT this. I don't know. Seems like the kind of thing we can JIT. And the reason I'm saying that is because, actually, I guess this is the kind of thing that is like computed statically anyway, because this just depends on shapes and not values. So I'm not going to bother to try to JIT this because I don't think it really makes sense. Like tracing will be just as hard as doing the actual computation. Does that make sense? Like this jax.tree.leaves is just going to go through the model and get the shapes or get all of the leaves. And then we're going to iterate through them all and get the size. And so at trace time, I would need to do this. I need to go through this with abstract JAX arrays. And then I would need to get the size. And I would need to add them all up. And I'm not sure how that would be faster to do that and then execute it. Like the computational graph might end up just optimizing down to just the number that we computed during trace time. And so we might as well just compute the number once. If we were calling this many times, I don't know, it might make sense to JIT it, but if we're calling it many times and we know it's always going to be the same result, we could just not call it many times. So yeah, I'm not sure what that is good for. But this model forward, we definitely want to JIT that. So when we're going to go to the architecture section, and we're going to want to wrap these in JITs and see if that makes a difference. Okay, we made the atom initialization. This could probably be JITted. I don't think there's that much initialization to do, but you know, might as well. Okay, the training loop. So the stuff that's going on here, we can definitely benefit from JITting, especially this value and grad operation. So this value and grad operation is happening every single time, all 256 steps of the training loop. We're redoing the automatic differentiation to get the transformed version of the function. It would be much easier to do that once at trace time and store the automatic differentiation inside the compilation cache, so that then every time we do the training step, we could then reuse the autograd that we did. And so this could definitely get a benefit from JITting this sort of training loop. Oh, and I'm seeing this is just finished with taking 1 minute and 13 seconds total. So that's a good baseline to have in mind. Okay, although I guess, you know, one thing that's a little bit confounding here is that I'm recording this lecture, which is using a little bit of my CPU to do the video encoding. So if that could create a problem later, but I don't think it will be a big problem. Okay, what about updating the optimizer? There was a bunch of array operations in there. We could probably JIT that update and get a little bit of a speed up. Okay, this stuff is not something that we can JIT. Working with Python lists is not generally something you can JIT because the computational graph is just going to be like a bunch of append operations or whatever. And if you put a different list into the function every time, for example, that would count as having a different shape because it would be, so a list is basically a pie tree. It would be like having a pie tree of a different structure. And that counts as part of the sort of shapes and D types. That, like, you could think of it as like the number of arguments would also be part of the compilation key. Okay, what about this visualization code? Same deal. So the batch accuracy, computing this, we can JIT the actual evaluation, but then all of this stuff that has to do with forming these plots, this is all stuff that matplotlib does, basically uses NumPy for everything. And it is not JITable. And also then obviously the printing that we want to do is a classic example of something that is not going to be JITable. But I guess we've got in mind a few things that we can try and JIT. So let's just go through and see if we can in fact do that. So there's not much going on here, but we might as well try and JIT this static method. So what if I just jax.jit? I think actually if we do that, we're going to find that it will give us an error message that says static methods aren't JITable. But when I encountered that message, I discovered that there's actually nothing stopping us from jitting it and then turning it into a static method. So just if you want to jit a static method, just make sure you do it in this order. This means that, I mean, we only do this once. I don't know if it's even worth jitting, but let's just do it. Let's just jit everything we can and see what overall difference it makes. So jax.jit of the update, this should be fine. Oh yeah, this is a good reason actually to have made our class a pie tree, because jax.jit is going to appreciate that the inputs are pie trees so that it can think about them in terms of the compilation cache. And if you have inputs that are not pie trees, then you generally need to use other tricks. You need to sort of configure JIT specifically to ignore them, and we'll look at that in future lectures. But at the moment, because we've registered this, I remember last time it was like unclear why we should register Atom as a pie tree. But one reason is so that we can sort of use JIT operations with this Atom object as an input, and that's a good payoff for that. There's a whole bunch of computations here. There's no side effects. There was no printing or anything, so this should be fine. This should JIT fine. Oh yeah, and we're calling it with the same shapes every time we call it. It's the same sort of SimpLeNet architecture, which is a very big pie tree, and all of the leaves have certain shapes. But every time we call it with the same structure. So it's going to just like walk over that structure, notice that it's the same as something in the compilation cache already, and it's going to use that precompiled thing and save some time. Okay, so what about what's next? So we've jittered that. It should work. Scaled tanh, you know what? Why not? Let's just wrap it in a jax.jit. Just jit everything. Okay, the affine transformation. Okay, one thing we could do is we don't actually need to jit all of these submodules, by the way, because it's enough to just jit the overall thing. But I just like to jit everything, because you never know when you're going to want to call into some submodule from some other part of the code, and then or like from like when you're testing or something like that. And if you're writing a unit test for this, you might as well want it to be jitted, and you want to make sure that it's jittable anyway. So we might as well do all of these jax.jit. And just checking the shapes that we call this. Sometimes we call this forward with different numbers of inputs. Remember, for example, the last two layers, we're going to be calling it with different inputs each time. So it is actually going to need to trace this multiple times. And Jax will just figure that out. But it's only going to have to call it with those, it's only going to have to compile it those like 2 times. And it will become all part of one big computational graph. And it will compile the whole thing. And so that should be fine. The initialization, again, make sure we do it after the static method decorator rather than, well, I should say, I guess, before the static method decorator in terms of the order that they're applied, but after in the code. So jax.jit should be the first decorator that's applied, because we can't JIT it once it's been turned into a static method. Oh, but something here is off, because these num inputs and num outputs, those are going to have to actually, be known at, those are going to be determining sort of the shape of some of the things that are coming out. So let me just see what I want to do about that. I think it should be fine. Maybe I wasn't jitting this, actually, and I was just jitting the top level thing. Yeah, I want to talk about how to deal with this situation later. And so I'm going to actually not jit these for now, because it's going to cause a problem in a little bit. I guess I can do the forward pass, it doesn't matter, but okay, I'm just going to skip all of these. And the subsample as well, and the simpleconv2d as well. And let's just jit the things that we actually use at the top level. And then later, when we learn how to do this properly, we can jax.jit everything we see. But today, let's just stick to these ones. And so the reason is because everything here is going to sort of work in the way that we want, in that we're only using the shapes and the data types and not the values. And so here we have self, which is a pie tree, so that's fine. Image, which is just an array. And then we're just doing a bunch of computation. And here we're jax.jitting the batch forward, we might as well also do, oh yeah, this is good because if we do this, then we're only going to do this VMAP computation once per shape. And so this is another example like the value and grad transformation, where previously every time we called batch forward, we were recomputing the VMAPed version of the function and then calling it. So it's just a little bit nicer if we can call that and then have it sort of memoized or cached, because if we call with the same shapes again, it won't need to VMAP again. That's nice. I do think it would be cool if VMAP also had a cache. I'm not aware that it does. So in some cases, you might end up VMAPPing and gradding your functions like multiple times. I'm not aware that there's anything stopping that, but I don't know, it could be, or it could be a feature implemented in the future. I haven't really looked into it. Okay, and then there's a net. We can also jax.jit this. So this was what I was kind of worried about, because there's a whole bunch of constants in here that are going to determine shapes later, and we need to know those at compile time, at trace time, in order to be able to compile. And they're all defined here, and I've sort of set it up this way, that they're all hard-coded into this initialization function. And so that should be fine, but if I was jitting those submodules separately, I would need to sort of mark that those inputs were to be treated as kind of statically known, assumed to be statically known. And we're going to look at that next lecture, so let's skip over that detail for now and revisit it later. Okay, going through a little bit more to the metrics section. So we can definitely jax.jit this cross entropy, and might as well also jax.jit this batch cross entropy. This is going to be called with the same types every time, because we're just using this for all of the training batches and computing the grad of it. I guess if we jit the training sort of step, then we're not going to need to do any of this jitting actually. But you know, anytime you wanted to catch this batch cross entropy, even maybe outside a training step, now it's going to be jitted for us. And that's another example where we're going to be caching the value of the VMAP as well. Okay, and so then we have jax.jit of batch accuracy. Yes, we can jit this function because we're going to be calling it with, this is the one we use for evaluation. So every single time we call it, and like outside of like the training loop, we call it in this evaluation stage with the same shapes, this like 1,000 times. So it's just going to be traced once, and then it will run a little bit faster every time. Noting that all of these functions are the ones that sort of contain the forward pass at some point inside them. So this would also be a case where we don't actually need to jit the forward pass. But if we ever want to test the forward pass separately, then it's good to have it jitted anyway. Okay, and then the visualization code, we can't jit this as discussed. It sort of uses NumPy rather than JAX. It does a whole bunch of stuff with matplotlib, which is about kind of moving arrays of characters around and stuff and calculating what characters should be on the screen. And this is not JAX code, so we won't jit this. You can sort of tell by the inputs, they don't look like arrays. I guess some of these inputs are arrays, and we do have the model, but this is just an example where we're going to call batch forward, and so it's good that that is going to be compiled for us because we wrapped it up above. And then metrics is the same. The inputs here have nothing to do with JAX. We've just got floats and ints and lists of tuples of those. And in fact, every time we call this function, even if we wanted to jit this, even if these were arrays, even if this was like a 2D array of floats, and then the ints could be represented as floats, then every time we called this function, we'd be calling it with a different shape, because these lists in the training loop are growing every time we append to them and we want to visualize them. And so that's another sign that JIT might not be appropriate, is if you're calling it every time with a different shape, because then it needs to do all this extra work to compile and then just to execute once. And we already saw when we were doing the elementary cellular automata in the overture that sometimes if it's a big enough computation, if you add the compiling time, the total time to compile and execute just once is lower than what it would cost in like NumPy, or certainly what it would cost for just JAX alone running without compilation. But in this case, I don't think that's going to be the case. We have pretty small data, and it would probably just slow us down even if we could JIT this. And once again, the matplotlib stuff is not generally stuff that's going to be jittable. It's sort of going to happen once, and it's going to be in the computational graph. The computational graph will be really big. That's the whole script. The one last thing that we wanted to JIT is the step of the training loop itself. That's a little bit tricky because it's not currently a function that we can actually put a decorator on. And we can't put a decorator on the main function itself because there's a whole bunch of side effects that happen in this main function. So what we should basically do is create another function to represent just the part of the code that we want to JIT. And so I'm going to sort of take this part of the code that does the sampling of a mini batch, the computing and the batch loss and grads, updating the optimizer and getting the model update and applying it to the model. And I'm going to just JIT that, and then I'm inside the training loop, I'm going to call it. And so this is sometimes a pattern that you will see in Jax code, where they sort of have a separate step where they initialize a training step. So def train step, and we'll figure out what the inputs and outputs are in a second. But the point is that I'm going to be able to jax.jit this. Okay, so let's figure out, without bothering too much about type annotations, what the inputs and outputs of this should be. Basically, what I want to do is I want to call this here. I want to see the net effect of this training loop was to, first of all, we're going to come out with a new overridden key, and then we're going to come out with a new overridden loss and grads, and then we're going to come out with a new overridden opt state and a new overridden model. Everything else is kind of local to inside this function. Actually, grads, I guess, is also local, but the loss is going to be used later. So I definitely want the inputs to be the current values of the key and the opt state and the model. And the outputs should include the key, the new value of the key, the new value of the opt state, and the new value of the model, plus the loss. So let's do that. Let's say key, opt state, model, loss equals train step of key, opt state, model. And now this will be a function that is kind of just actually doing the jittable computation of the train step. And then this, we're going to need to actually define those arguments. So we should have key, opt state, and model as inputs, and then tuple as output. And I'm not going to fill in the details of the tuple. In fact, I won't even bother to annotate it at all. It's sort of local enough to the code that I feel comfortable doing this. Let's call this defining the training step, just to sort of match our pattern of printing out what we're doing at each step. But we know that this computation doesn't actually happen now, so this should be a very fast step. It just needs to define the function and place a wrapper around it, and the actual computation is going to happen during the first training step itself. So we might notice that also. It might just stall for a second before it starts printing things out. Okay, so after all of that, we may have made some typos or mistakes somewhere. We're going to see if there are any errors, and we'll learn how to handle them together. But, you know, maybe I'm feeling optimistic. So let's just see whether this works. Initializing the model, so far so good. We haven't actually, okay, here's an issue. I didn't return. Yeah, that's a big issue. So I need to actually, I knew I needed to do something here. I knew I was missing something. So key, opt state, model, loss. Okay, the reason I knew this is because it's saying cannot unpack a none type object. So it's like the train step is returning none, but I wanted it to return this for tuple, and so I must have forgotten to return. Sorry about that. Let's try again. Feeling optimistic again. You know, you just keep feeling optimistic. Maybe one time you'll be right. Okay, we made it to the training step. It looks like it's doing something. Hasn't started printing outputs yet, but maybe it's compiling everything. Okay, it's compiled everything. It's running. I can't tell if it's running faster. We'll have to wait until the end. We're timing this, so we'll see how fast it went. We did some of the compilation up here when we initialized the model, because I think we compiled the init method. We did some of the compilation when we did the forward pass here, and then we would have done the rest of the compilation for like the batch cross entropy and so on the first time in the first step of the training loop, and then subsequent steps would in theory be faster. This should be, by the way, getting identical scores, so we should end up with like 93.4 at the end. Interesting. For some reason, we haven't ended up with the same score as before, so I'm not sure exactly what's going on there. I might have to dig into that. Just let me check. Did we definitely get the same score here? 94.9. Yeah, we did. I really expected us to get the same score after jitting, because jitting shouldn't be changing the order in which we're using any of the randomness. So that's quite interesting, slightly concerning that we've made some kind of mistake. But anyway, we have wiped off 23 seconds off the clock because previously we were taking 1 minute 13.86 and now we're taking just 50 seconds. So 23 and a bit seconds wiped off. So that's not bad. It's not 10 times faster, but this is a pretty small model. And there's actually a lot of this code that was happening, loading and so on. If we trained for longer, I think the sort of bottleneck would be getting a better payoff from this. And also if we're training a larger model, and also if we're training on like bigger hardware than my laptop CPU. So yeah, I'm really not sure about this performance though. So I'm going to have a think about what's going on there. It's kind of weird for it to be giving different values at all. So slightly concerning. Also, I'm noticing that the model that we get at the end is it's also different because previously we classified this one right and this one wrong. And now we've got it the other way around. So yeah, don't know exactly what's going on there. But I'll dig into that. And then I'll maybe post an update or something if I find out what's going on. Otherwise, maybe you could figure out what's going on. Okay, so I think we're ready to wrap up now. This runs a little bit faster. We sort of slash the computation time down. This is going to be useful going forward. We're going to be working with code that is running. Oh, okay. You know what? I just had an idea that maybe we did change the order in which we're using keys or something like that. Let me just check this before we wrap up and give the challenge. Because we defined this function here, let's think. So this key is coming out, and then it's splitting it up. That should be the local version of the key, but there could be some spooky thing going on with like scopes and like non-local variables or something like that. I think it's not the case. I think this is like the right way to do that. Everything is happening in the same order with respect to the randomness because everything was going on in this part of the training loop. That was happening. There's really nothing else that we changed. Okay, I'm mystified again. I thought our code was going to be deterministic. It really should be. And it is possible that running the compiled versions of the code is like different up to numerical precision or something like that, but we're seeing quite a difference in the output. So I'm not so sure about that being the case. Yeah, okay, I'm going to declare this a mystery again, and I'm going to look into it. If you can spot what's going on, please let me know in the comments. Otherwise, I might post a comment if I figure it out. Okay, let's leave you with the challenge for today, and then wrap up. So the challenge for today, we've learned a bunch about JIT. We spent a bunch of time in the JIT dojo, and so hopefully we're starting to understand like the process that a function goes through when different things happen when we JIT. In the upcoming lectures, we're going to use this to build sort of some bigger models that run still pretty fast, and we're going to explore more nuances about how to compile different types of programs that maybe we want things to depend on the values rather than just the shapes and data types and so on. We're going to explore more about the compilation cache and how it's keyed. But for now, I think we have enough. I think you have enough to try exploring different architectures here. This will also be a good revision of some of the stuff from the last act on sort of fundamentals of pi trees and so on. If you could implement a residual network, which if you study deep learning, you'll sort of know what this is from computer vision, or just basically a bigger convnet, implement a bigger convnet, and then make sure you can get it to JIT. So make sure that you have implemented it in a way that you don't get any errors when you try and JIT it. And then see if you can get it to run on this data set and see if you can get a higher accuracy. I mean, ideally, it should also be a deterministic accuracy. I'm just going to run this one more time to make sure this is actually deterministic within itself and there's not some other weird thing going on. Anyway, yeah, so that's the challenge for today. Yeah, I think you can have some fun with it. There's a lot of flexibility to this challenge. You can sort of go and implement like something like AlexNet or a residual network that would be a little bit deeper. Some of these might require like a faster processor to run. You might want to see if you have access to a GPU, if you can install JAX to the GPU and run it there instead, and you would get sort of faster results than running it on a CPU. Yeah, let's leave it there. So this mystery persists, but at least it's deterministic, it's reproducible. It looks like we've got the same learning curve as last time with these sort of peaks and so on, and 92.5 is the final thing. Similar time again, so I guess that was it's a reliable-ish estimate. Let's wrap it up there, and I'll see you in the next lecture. Good luck with the challenge.